Hello class. Today we are going to look at on recursion relations for Legendre polynomials. First, we're going to look at Rodriguez formula, where we have learned before about the Leibniz rule for differentiating products. Okay. The Rodriguez formula is given by the one in the yellow box. So let's see, this is equation 1. So you have P respect to L for L integer, and this P is a function of X. It is the Legendre polynomials, that is the solutions for Legendre differential equation. Okay. You can find, for example, let's say choose L equals to 0, then everything takes L equals to 0 is just 1, and you get the first one is 1. Okay. Thus, you may work out for P1, P2, and so on. So it is very straightforward. Next, we are going to look at generating function. So you have to focus on these two definitions. Let's say this is equation 2 and this is equation 3. So these are functions of uppercase phi here, functions of two variables, 1 and 2, okay, given by the following: 1 minus 2xh plus h square to the power of minus half. And the other one, you can also write these functions as series. So that's why they call this series solution. Okay. H over here is actually just a dummy index or some kind of like an identity. Okay. And we're going to use this X and H to derive other recursion relations. Okay. A new term that you will learn is about recursion relations, or similarly equivalent to recurrence relations. Okay, either recursions or recurrence. So you're going to use the generating function, equation 2 and 3, to derive several recursion relations up to F, A until F. So today we are going to derive the first one, and later on in your you try it, you're going to submit in terms of B. So now let us try to look at how we're going to do this. So we're going to use these first relations of, we're going to take a partial of uppercase V respect to H. Okay, so this is just looking at H, then you're going to use the 1 minus 2xh plus h square minus half. Okay, and your H is always less than 1. Okay, so yes, it should be less than 1. Okay. And then, so what do you have here? So you just differentiate respect to H partial, so your X, treating X as constant, so you have minus half. You have 1 minus 2xh plus h square minus 3 half. Then you have to multiply by what? Minus 2x plus 2h. Okay, so you just can simplify. So if you simplify, you have x minus h, and then I wrote it like this, plus h square minus half, and then I have another terms plus h square minus 1, like that. Okay, and you notice that you have here is actually your phi xh. Therefore, you can write x phi xh, but then because of this is minus 1, so you can bring it on the left hand side. So you have 1 minus 2xh plus h square multiplied by that. Okay, so you prove this first. So next we have these relations. Let's put this number 4. Okay, so remember we are going to use equation 3 in terms of the series and substitute in 4. Equation 4. Okay, so what do we have? So you have 1 minus 2xh plus h square, and then over h of the sum, okay, hl plx, and then you have x minus h sum L0, and then you have h plx. Okay, so later on maybe I just drop x, I just drop pl, so I just wrote down this plx. Okay, just to have a compact writing. Then we proceed. So what do we do? So you have 1 minus 2xh plus h square, and then you partial derivative respect to hl, and then you have hl minus 1 pl, where you still have the sum. Then you have to start with 1, okay, because you have differentiate one time, and then you can just expand this series, okay, and then you have hl pl minus L0 hl plus 1 pl. Okay, so you have to equate here. Okay, you have to equate coefficients. Okay, with respect to hl minus 1. Remember, we want the sum and also the power of h respects to the same footing. Okay, so you can expand first the right left hand side. Okay, so you still have L1 L hl minus 1 pl minus 2x L1 L hl plus 1 plus h minus 1 h plus 1 minus 1, and then you have pl plus sum L1 infinity h minus 1 hl minus 1 plus 2, okay, pl. Okay, so you can make this is your right hand side, so you have x L0 hl pl minus L0 hl plus 1 pl. Okay, so and then you have L minus L equals to 1 0 L hl pl. You clean these calculations, all right, and then you have L hl pl plus hl plus 1 pl x L0 hl pl minus 0 0 HL plus 1 PL. Okay, but remember I want HL minus 1. So you make the order all HL whatever of L prime must be L minus 1. Okay, so L prime must be L minus 1. So what do? So L1, L minus 1. Sorry, this is minus 1, so you don't do anything. Alright, you don't do anything for this because it's already minus 1. So you have L, HL minus 1 PL. So you change the second term, L equals to 1. So you have L minus 1, HL minus 1, PL minus 1. So what do you do for the third term? You want L minus 1. So you have, oh sorry, I miss L here. Okay, so I have L here, and then let me do that carefully. So I have L minus 2, so I have H L minus 1, and then I have P L minus 2 equals to X L minus 1, because I'm choosing H L minus 1 here, P L minus 1, and then the other one is plus minus L1 HL minus 1 PL minus 2. Okay, so next we simplify. So you can just minus 1, put like this, HL minus 1, make it equals to 0. So what you have? LPL minus 2x. Look at same footing, HL minus 1, PL minus 1. So you have 2x L minus 1 plus x PL minus 1, make it equals to minus L minus 2 plus 1 PL minus 2. And then you have PL equals to 2L minus 1x PL minus 1 minus L minus 1 PL minus 2. Okay, so this is the same as your star. Alright, so the idea would be you have to be very careful at when you're handling the order of your H. So let me remind you again, you have to substitute properly your generating functions, equation 1, equation 2, and equation 3, and you are going to try to prove B with the instructions given in the you try it. Okay, alright, thank you.